In Unit 5, Learning Set 3, we're going to go over exponential functions. And our objectives are to evaluate exponential functions, graph exponential functions, and solve exponential functions. So we're going to review the law of exponents first. If s, t, a, and b are real numbers with a greater than 0 and b greater than 0, then a to the s power times a to the t power equals a to the s plus t. So when we are multiplying exponents that have the same base, then the exponent values are added. So an example would be 2 to the third times 2 to the n would equal 2 to the 3 plus n. And if we're using it a to the s power to the t power, then we're going to multiply those exponents. So it becomes a to the s times t. So if we had 3 to the 4th power taken to the 5th power, it would be 3 to the 4 times 5, or 3 to the 20th power. AB taken to the s power, we could split it apart and make it a to the s power times b to the s power. So whenever we have something contained within parentheses, each individual item within that parentheses is taken to the power outside of it. So for example, if we have 4x to the 3rd power, it would be 4 to the 3rd power times x to the 3rd power. 1 to the s power equals 1. So 1 to any power always equals 1, because 1 times 1 times 1 times 1 is always 1. So if we had 1 to the 3rd power, it would equal 1, because 1 times itself 3 times is 1. The 5th law of exponents is a to a negative power. So a to the negative s. When it is a negative power, it's telling us to flip and put it on the opposite side of a fraction. So a would be considered the numerator. So if we have it to the negative s power, that means it would become 1 over a to the s power. Or we could put it in parentheses, 1 over a to the s power. So an example would be 5 to the negative 2x. So it would be 1 over 5 to the 2x, or 1 over 5 taken to the 2x power. A to the 0 power, that's our last law of exponents. So anything taken to the 0 power is always going to equal 1. So 5 to the 0 power equals 1. I could take 8 to the 0 power, it equals 1. I could have x to the 0 power, and it's going to equal 1. It always equals 1. Okay, so identifying linear or exponential functions, and we're looking at tables. So we want to determine whether the given function is linear, exponential, or neither. So what we want to do is we want to look at two things. We want to look at the average rate of change, which is basically our slope, the change in y over the change in x. And we also want to look at the ratio of consecutive outputs. So that means we would take two outputs in a row and divide them. So the average rate of change, for example, on this first example, I would take 6 minus 2 over negative 1 minus 0. So I'm using these two rows together to find the first one. So the second one, I would be taking 2 minus negative 2 and dividing it by the x values of 0 minus 1, and that gives us negative 4. We would continue on doing the same thing for the next several rows because we're looking for a pattern here. Okay, we're looking for a pattern. Now, when it comes to the consecutive ratios, we would take, for example, 2 divided by 6 is 1/3. negative 2 divided by 2 is negative 1. And then those would be our next values. So we want to look at this and we want to analyze it. Well, if all of the average rate of change are the same values, that tells us that it's constantly going up at the same rate. So therefore we have a linear function. In this case, we do not have consecutive outputs, and that would be representative of an exponential function. So our average rate of change in this case was negative 4, and that's our slope. Because remember, we said the average rate of change represents our slope. And we would therefore know that our y-intercept when x equals 0 is 2. That's our b value. So because it's a linear function, we will be writing y equals mx plus b format. So we can take our m and our b values, plug it in, and now we have the equation for our linear function. So let's look at identifying this next table. Follow the same steps. Find the average rate of change for each combination. Okay, so in this case, we can see that our average rate of change is not the same. Okay, so therefore we know it is not linear. Let's check out the ratio. So if we take 27 divided by 81, then we get 1/3. And we go down to the next set of 2. We take 9 divided by 27. That also reduces to 1/3. And our next two amounts reduce to 1/3. So based on this, because the ratio of consecutive outputs is the same, then we know that this is an exponential function. Okay, so an exponential function uses the format g of x equals c times a to the x power, where c represents our initial value. That's what we started at when x was 0, so that was 27. The a is our ratio that we discovered over here. That's our 1/3. And then we just simply plug it in. G of x equals 27 times 1/3 to the x power. And that would be the representation of our exponential function in the table.